This video looks at the idea of an energy momentum tensor and how it describes the distribution of matter and energy in space-time. It achieves this by deriving the tensor for a swarm of non-interacting particles on some Lorentzian manifold. Alright, so let's look at the form of the energy momentum tensor in this video, and let's go right back to the beginning. And it's the source term on the right hand side of the Einstein field equations. On the left we have the curvature, on the right we have the source of that curvature, the matter and energy distribution. This is a rank 2 tensor, and this tensor describes the matter and energy distribution that is the source of curvature. And what we're looking for is a form invariant under a transformation of coordinates. It's a tensor, so it has the same form in all coordinate systems, and in that way it obeys the general principle of covariance. Now what we're going to do is look at the form it takes for a swarm of particles, or otherwise known as dust. And it's also called the stress energy tensor. So let's start with some fixed observer in a reference frame, and in the same reference frame at rest with respect to the observer is an object, a little red ball here. And in this there's no relative motion between the observer and the ball or object in this frame. And in this frame the ball is at rest with respect to the observer, and so the total energy of the object, the ball here, is its rest mass times c squared. Now, we could also look at it this way. The forward velocity of the observer and the forward momentum of the object are given by, so for the observer, the forward velocity in this frame is this, the spatial components are 0, and the forward momentum for the object is this, E on C, and the spatial components 0. Alright, now let's start by forming this relationship, the forward momentum with the inner product, scalar product of the forward momentum with the forward velocity of the observer, and we have this object here. We've only have the 0 components involved here, the rest, all the other spatial components are 0, so the time components are non-zero, and when we in flat space-time we use the Minkowski metric, this one here, eta mu nu, and the only terms we need to consider are the 0 terms, the time components. And when we multiply that out, we have minus E on C times C, so that's E on C times C here, that's these two components. We started with a negative of this inner scalar product, but also with eta mu nu, the 0 component of that metric here is a negative as well, hence the double negative. This gives us positive, as energy should be. And we have here the Minkowski metric, this diagonal metric here, -1 in the leading term. So for our fixed observer, fixed in the frame S, we can say that the observer can attribute to the mass, the red mass we saw earlier, an energy equal to minus P, the forward momentum of the object, dotted with the forward momentum of the observer. Alright, now let's put the object or the mass in a different frame, inertial frame, moving with respect to the first frame. So the object is now in frame S prime, and it's moving with respect to the fixed observer with a constant velocity u. And so the relative speed between the mass and the observer in the inertial reference frames S and S prime is u. That's the relative speed. And we have now gamma is greater than 1. We have frame S prime moving with respect to frame S. They are in standard configuration, so the two x, the x1 and x1 prime, or the x-axis, coincide or collinear, and frame S prime is moving with constant velocity u with respect to frame S, so standard configuration, and the object or mass is in frame S prime. Now the forward velocity of our observer is still c00, the spatial component here is 0, just the time component is c, gamma is 1 because the observer is not moving, is at rest, and the forward momentum of the object now has a gamma factor, and the spatial components are non-zero. Now again, same relationship, the inner product of the forward momentum vector with the forward velocity u, negative in front, is this object. We expand this out. Alright, and when we put that in, we again get plus E for the energy. Now this time the energy is m0 gamma c squared, so that E is now the rest mass of the object, the red ball, times a gamma factor because it's moving with respect to the observer, and c squared. So from the point of view of the observer, he/she records an energy E is m0 gamma c squared. And again we have E equals minus p dot u. Handy relationship. Now, Robert M. Wald's book, on page 69, he says of this equation, the energy of the particle as determined by an observer who is present at the event of the particle's world line at which the energy is measured is again that relationship, E equals minus form momentum dotted with the forward velocity, where VA is the forward velocity of the observer. In Misner, Thorne and Wheeler's book, Gravitation, on page 134, they refer to in a box to a box in motion, our red ball if you like. The energy in the box as measured in its rest frame is minus the projection of the form momentum on the box's forward velocity. Again, this relationship. And in Misner, Thorne and Wheeler's book, they have an object containing a certain amount of matter and energy, and the observer makes an observation of the total energy inside the box at some point on the box's world line. But what they've done there is minus the projection of the form momentum on the box's forward velocity, and this is the form momentum of the box. Now, according to their definition, we then have the energy of the object as measured in its rest frame is minus p dot u. Notice here, this is the form momentum of the box, minus m0u. So the spatial components here for u will not be zero. And the form velocity, of the box, again, the spatial components here will not be zero. And these two will, of course, be the same, hence uu. And, as we well know that u, the forward velocity dotted with itself, the scalar product, the forward velocity with itself is minus c squared. I've shown that in a separate video on this channel. The minus out front here cancels with the minus c squared, and again we have positive value for energy, m0 c squared, and that's in the rest frame of the box. Now this would also be the case if the observer shared the same forward velocity as the box. In other words, the observer's in the frame of the box. All right. Okay. Now we're going to go a step further. Instead of having just a single particle, our red ball from earlier, we're now going to have a swarm of non-interacting particles in some inertial or Lorentz frame S prime, which is moving with constant velocity with respect to some other inertial frame S. So here's our inertial frame S with the observer in it. Here's our swarm of particles moving, non-interacting particles moving with a common velocity u in the frame S prime. All right, now in the rest frame, that was S prime, forgot there, or the co-moving momentary rest frame is another way of saying that, this swarm of particles, we can more easily work with its local density, because now that we have multiple particles, we're not going to work with the energy of one, but we're going to work with the energy of the total, and then we're going to have a look at the density. It's often makes more sense to work with density than it does to try and sum up all the particles. So let's say for our swarm we have n equals, n is the number of particles. V is the volume element in the rest frame of the particles. So volume element delta x, delta y, delta z. And the volume is those three multiplied together. Now this is in the rest frame of the particles. So this box is at rest with respect to the particles in this particular case. All right. But how do the densities in two different reference frames moving with respect to each other compare? So let's say here's our rest frame here, all right, and here's the same box in some inertial reference frame in standard configuration with the first one here, moving along the common x-axis with a constant velocity u, or constant speed u if you like. And this second frame here, what will the box look like to an observer in this frame S? So this box here, delta x, delta y, and delta z is suppressed in these diagrams here. This is now placed in this second frame S prime, which is moving with respect to the frame S with velocity u. And when that happens, the observer here, this over here, our observer here, she notices that the length in the direction of motion is Lorentz contracted, and the other lengths in the y and z directions are untouched. So in frame S, our density, if all our particles were inside this box, would be the number of particles divided by the volume in this frame, which is n over delta x times delta y times delta z. But what will this observer observe in relation to this box over here? So identical box moving in frame S prime past S along the common coincident axis, so standard configuration. Here n prime, an observer in n prime would measure n number of particles, same as in this frame here, over v prime, and that would be n over delta x dash, delta y dash, delta z dash. That's an observer in here. Now, but transformed to this coordinate system, this observer would then measure this, n over delta x on gamma times delta y delta z, and when we next step in algebra there, this reciprocal relationship, and this ends up on top, and we get n prime is gamma n over delta x delta y delta z. So this observer here, for the box moving past her, records a density of gamma times n over delta x times delta y delta z, whereas for the box in her rest frame, she just records n over the volume, delta x times delta y delta z. Alright, so we can use our volume element and the 4 velocity of the swarm to define a number density 4 vector. N is n over v times u, where the components of this, n's upper subscript mu, superscript mu, contravariant components, if you like, n over v times gamma c uxy uy uz. Okay, now the 0 component gives us numerical density. N0 is n over v, u0 is n over v times gamma times c. This is the number density. We have that factor of c in there, which is because it's a component of a vector. Now, as we've just seen on the previous slide, that in the rest frame of the swarm, gamma is 1, and so our observer, she noticed that there was no Lorentz contraction to consider, and for her, in her rest frame S, N0 is n over v times u0, which is n over v times c. There's no gamma factor. Whereas she observes in frame S prime, she observes n over v times gamma times c for her number density in S prime, and in S she observes just n over v times c. Now notice in the rest frame, minus p dot n, minus the Minkowski metric, p mu n nu, only the 0 components show up, and we have this object, n over v times e is now n times e. Remember, there are n times of particles. If e, and they're identical particles, I didn't mention that earlier, but identical particles, we have n lots of them, so n times the energy of one of them is the total energy over the volume. And this we now have is an energy density. It's the total energy of all the particles, all the identical particles, n number of them, over the volume element. Okay. Now, in the case of some observer with the same 4 velocity as the swarm, just like Misner and Thorne had, you could do the projection of the form momentum of the box or the swarm of particles on the number density vector, and we would have minus m0u dot n on v times u, minus n on v m0 u dot u. Well, u dot u is minus c squared. This minus and that minus cancel, and we're left with n over v m0 and times c squared, and m0 c squared is the energy of just one of the particles, but we're now going to multiply that by n of them over v, and again we have the total energy over the volume, which is the energy density. Now coming back to our number density 4 vector, the x direction component in the number density 4 vector is nx is n over v gamma ux. So that's the density in the moving in the direction of the x-axis. All right. Now imagine some of the particles move through our stationary volume V in frame S. So the box now is in frame S, and the swarm is in frame S prime, and the axes are not shown here, but it's moving through in the direction of the x-axis here, and the swarm is moving through this stationary box here. So this box represents a volume element, and some of the particles are moving through. This volume element can be any size. It doesn't matter what it is, but it can be any dimension we want. But so we'll call it volume element, delta x times delta y times delta z. The swarm of particles is moving in the direction of the x-axis. So this is frame S, and the blue particles belong in frame S prime. All right. Now the surface here, this delta y delta z surface, is perpendicular to the x direction. It's a surface of constant x value, and the perpendicular to which points in this direction where the red vector ex is pointing. All right. So some of these particles will cross a surface whose perpendicular or normal vector points in the x direction, shown here. All right, so let's have a look at the number density 4-vector component for the x component. Nx is n on v gamma ux, is n on v gamma delta x on delta t, is n gamma delta x on delta x, delta y, delta z, which is the volume element, times delta t. Now this delta x and that delta x cancel, and we get n times gamma on delta y, delta z. Delta y, delta z is this area element, is n times gamma on the area element, surface area element, times the time interval. So it's a flux. All right, so here are our particles, some of our particles passing through our element of volume, okay, and this box is stationary in the S frame, and the particles, the blue particles, belong in the S prime frame, and they're moving through it. And this surface area here that they're passing through as they move to the right there is equal to delta y times delta z. All right. So in the x direction for our number density 4 vector, we have n gamma on delta a delta t, which is the number of particles in the x direction times the gamma factor over per unit of area per unit of time. And what is that? But nx is just the flux of the particles in the x direction. It is the number of particles crossing per unit of area of surface area perpendicular to their direction of motion per unit of time. And hopefully my diagrams have made all that clear. Just another thing about the number 4 density vector is n dot n, the inner product with itself, is n on v times u dot n on v times u. U dot u is of course minus c squared, and we end up with n over v all squared, and the minus here from the u dot u is minus c squared, so we get minus n on v all squared times c squared. So we have that the total energy over volume, or the energy density, is minus p dot n, where the E total is just n times the energy of any one of the particles. They're all identical particles, so the energy of one times by the number of particles gives us the total energy. In the rest frame, we can define the energy density in the rest frame as being m0 n on v, right? Then in the rest frame, E total on v is n m0 on c squared on v, which is just rho 0 nm0 on v, which is rho 0 times the c squared. So rho 0 c squared is our energy density in the rest frame. That's in frame S. In some other frame, n on v, it has to be replaced with a gamma factor, gamma n on v. So our observer in S, making measurements, making observations, will need to include the gamma factor. Their results will be affected by that gamma factor. They must include that. Also, the mass is moving relative to an observer. So in the mass is a mass in frame S prime moving with respect to frame S. The observer in frame S must include a gamma factor as well for the mass. So just as we have E equals m0 c squared in the rest frame, we have E equals m0 gamma c squared for the observer in S frame, observing, making observations of objects passing him or her in frame S prime. That has implications for density. So the density becomes rho for the observer in S watching the particles go by. The density will be gamma m0 times gamma n on v, which is gamma squared m0 n on v, which is gamma squared rho 0. Right? In the rest frame, there's no gamma squared for the density, but in some other frame moving with constant velocity with respect to the first, then this other frame for the observer in the first frame, S, will come up with a density rho, which is gamma squared times the rest frame density. Okay, so we can write the energy density as E total on V is gamma squared rho 0 C squared. That gives us a total energy density, where minus P dot N is E total on V. So I think I've hammered home that point enough that this is the energy density here. All right, now we're in a position to define the energy momentum tensor for the swarm of particles in their rest frame, as the tensor is the outer product or tensor product of the form momentum of the particles with the number density vector for the particles. Okay, when we do that, we can just rewrite the momentum vector, 4 vector as this, the tensor product, n on VU, the number 4 density vector, number density 4 vector, I should say, and m0 n on VU by U, U cross U, the tensor product, and not the vector product in vector calculus. I don't mean that. This is the tensor product, and we'll see what that means shortly. m0 n on V components, basis vectors, and again components here, contravariant components, and the covariant component basis or the tangent basis vectors here. And again, just collecting terms, a little bit of algebra here, just pulling things over here, keeping the tensor product for the basis vectors here, and rewriting m0 n on V as rho 0. We're in the rest frame, this object here. And then we can tidy all this up by expressing it as here are the components of this tensor. This rank 2 tensor has 2 components so it is a 2, 0 tensor, 2 components upper in the contravariant position, U and mu and U. All right, and the energy momentum tensor for the swarm of non-interacting particles can be expressed in this form, or this one, or this one, all the same thing. So let's write it out with components now. Let's look at the components, T mu nu, the 2, 0 tensor, both components up. We get rho 0, U mu, U nu, and writing those out, we get 0, 0, 0x, 0. I'm using 0 for time instead of t, but I'm using, in Minkowski space here, I'm using x, y, and z for the components in Minkowski space. I'll just choose to, instead of put a t there, I'm choosing to use a 0. Okay, I hope that's all right by everyone. And you write out the individual components. Here we go like this. Now in the rest frame, we notice that all of these ux, uy, uz drop off. The only things that remain active are u0. And so that takes out all of these terms except for this top one here, which is the time component. And our tensor components, the only component that exists for this tensor in the rest frame is rho 0 c squared, this one here. Just hence in the rest frame. It's something different elsewhere, as we've seen in other frames. All right, so to understand what the individual components of this tensor represent, let's write the tensor in the form this, like this, and instead of u's, we'll use the form momentum and the number density 4 vector here. And writing those components out, we get all this instead. And we notice that the momentum 4 vector is E on C with the spatial components of momentum, and the number density 4 vector has these components here. The T00 component, T00 is P0, N0. Well, P0 is E on C. N0 is N on V gamma C. Now, here, when we say E, we need to expand that a little bit further, because if we're not in the rest frame, and clearly with a gamma there, we're not in the rest frame, so this has a gamma factor too. So it's M0 gamma C squared on C times N on V gamma C. And when we collect the gammas, we can have gamma squared N M0 on V C squared. And again, we have gamma squared rho 0 C squared. And that is, just as we found earlier, the energy density. An observer in frame S, remember our woman, she was observer in frame S, she saw another frame S prime going by. For her, the energy density will be this object here. that's what she will see. Observe. This is the energy density of the particles. This is our swarm of particles, and this is their energy density right here. Okay, next bit. The Tx0 component, Tx0 is Px n0, so the Px component is m0 gamma ux times n on v gamma c, just as before. And collecting the gammas, we get gamma squared nm0 on v times cu, so that's gamma squared rho 0 times c times ux. And this is the momentum density times c in the x direction. It's the momentum density in the x direction. Because remember, this is rho 0, the density in the rest frame. This is gamma squared because now this is the density in some other frame, moving with respect to frame S, and times this factor of c, and it's in the x direction, so the motion, if you like. So this is the mass times the velocity, momentum, times a factor of c. So it's the momentum density, rho 0 density. It's not just mass, but it's mass over volume, so it's density. So it's the momentum density in the x direction times a factor of c. The other component now, the 0x component, is T0x is P0nx, which is E on c times n on v gamma ux. Now again, the gamma here means that we're observing something in a frame S prime moving with respect to us, so E has a gamma factor as well, m0 gamma c squared on c times n on v gamma ux. Collect the gammas, gamma squared n m0, so that's our mass here, times c squared all over v times 1 on c. Now this is our energy, because it's got the c squared factor here now, it's our energy density times 1 on c in the x direction. Alright, so E total on V times 1 on c ux, and this is the energy flux times 1 on c in the x direction. So the energy flux in the x direction. Just one other thing to notice, Tx0 is Px n0. We can write that as gamma squared rho 0 times c times u, which is what we had up here. All right. Now, if I put in an extra factor of c in here, this becomes the energy density times 1 on c ux, and so we see that this one here is actually just this one. So these two things are saying the same thing. All right, they are the same thing. That whether you have the momentum density in the x direction or the energy flux in the x direction, it's these factors of c and 1 on c which make for a difference, but they mean the same thing. All right, you actually end up with, if you put this extra factor of c in here, you take this c over here and put an extra factor of c and then multiply by 1 on c, you see that this component is the same as this component. All right, next bit. The XX component, Txx, is Pxnx, m0 gamma ux times n on v gamma ux, gamma squared, nm0 on v ux. Well, that's interesting. Now, so we've got gamma squared nm0, delta x, delta y, delta z, and we'll write that first ux as delta x on delta t. Cancel the delta x's, and left with gamma squared nm0, delta y, delta z, well, that looks like an area, times delta t in the x direction. Well, gamma squared nm0 delta a times delta t, so the amount of mass per unit area per unit time in the x direction. This is the rate of flow of the x component of momentum, mass times the velocity as momentum per unit area per unit time. So this is the rate of flow of the x component momentum per unit of area in the x direction. All right, rate of flow meaning there's a time component because it's a change in a quantity per unit of time. This is just the x component of the momentum flux in the x direction. So in general, T alpha nu, upper or lower, is the rate of flow of the alpha component of momentum per unit of area in the nu direction. All right. So in the case of alpha equals v, we have another interpretation. Okay, we have now Px nx gamma squared nm0 delta A delta T ux. All right, let's hive a few things off here. Gamma squared nm0 on delta A, and we'll take this ux on delta T. And velocity, and over a small interval of velocity over a interval of time, you could see as the acceleration, right? I mean, ideally it should be a change in u from one point to another, but yeah, delta u over delta t is the acceleration. Well, this is the mass times acceleration and a gamma squared factor, so that's the force in the x direction, hence perpendicular sign there. So that's the force in the x direction divided by the area, delta y times delta z. Delta A is the area, so it's the force over the area, the force per unit of area. Well, force per unit of area in the x direction here is the pressure. So that's the pressure. Now, where alpha and nu are not equal, we then have shear forces. We have a pressure at work, but we have them acting, here we have x in the direction of x. So this is the pressure in the direction of x. This is the force per unit of area in the x direction. That's the pressure in the x direction. But if you have pressure in the x direction, the x component of force in the y direction, then you're going to have shear forces at work. I haven't gone fully into that, but you can see here that the diagonal terms txx, tyy, tzz will be pressure terms. All right, so in summary, the energy density, this bit in red here is the energy density. This row along here is the energy flux times a factor of 1 on c. And you can see how that factor of 1 on c is useful when we want to compare these. And we have in the vertical area here the momentum density times a factor of c. Here in the yellow bit we have the pressure terms that I just spoke about, and these in purple are the shear forces. And that's it.